You know that feeling, right? You're stuck in traffic, just staring at a sea of red brake lights, thinking there has to be a smarter way to do this. Well, what if I told you the answer isn't about more asphalt, but about more processing power?
Yeah, why are our cities so gridlocked? It's a question we've all probably yelled in frustration at our steering wheels. It's become this daily nightmare that just feels impossible to solve. But to even start fixing it, we have to understand the chaos on a massive, massive scale.
So, first up, let's talk about the urban gridlock, because this isn't just about being late for work. The real cost of all this congestion is actually pretty staggering. I mean, think about it. All that time we're just sitting there not moving, it's a huge drain on our economy. And every single one of those idling engines is just pumping out pollution. And honestly, it just makes life worse. It adds so much stress to the start and end of every single day.
Okay, so here's the real pickle for city planners. You want to test out a new idea, right? Like, what if we change the timing on these traffic lights? You can't just go out and do it, you'd cause chaos. You need a simulation. But trying to model millions of individual cars, all moving at once, that is an unbelievably tough computer problem to solve.
And that brings us to our second section, simulating the standstill. See, for a long time, the way we've tried to model traffic has relied on a method that's, well, it's really starting to creak under the pressure of our modern megacities. It really all boils down to two different approaches. Over on the left, you've got your traditional method, sequential simulation. Just think of it like a computer working through a to-do list, one item at a time. On the right, though, is parallel simulation, where the computer tackles a whole bunch of tasks all at once. You can probably see where this is going.
And this analogy is just perfect. The old sequential way, it's like one very stressed out chef trying to cook an entire 5-course meal all by themselves. They have to chop the veggies, then boil the water, then sear the steak, one task at a time. The whole thing just grinds to a halt. It's super slow and just not efficient.
So, if our single chef is totally overwhelmed, what's the answer? Well, this is where our new strategy, the parallel approach, comes into the picture.
Right, so instead of one chef, parallel computing is like having a whole team in the kitchen. The huge, messy job of simulating an entire city's traffic gets broken down into hundreds or even thousands of tiny jobs. You have one part of the computer handling the traffic lights, another is in charge of moving the cars, a third is putting new cars onto the roads, and the amazing part is, they're all doing it at the exact same time.
So what kind of tasks are we talking about? Well, while one little process is busy figuring out how the cars on Main Street are moving, another can be adjusting the light timings on Fifth Avenue, and a third can be looking ahead and spotting a potential traffic jam forming downtown. It's all happening in sync simultaneously. And that's really the secret sauce here. By splitting up all that work, the simulation just doesn't get overwhelmed. It can juggle way more cars, way more complexity, and it doesn't slow to a crawl. It can finally give planners the kind of real-time data they've been dreaming of. Okay, on to Section 4, Performance Gains Unlocked. Now, this all sounds great in theory, but does it actually, work? Well, the results are in, and honestly, they're pretty spectacular.
This quote from the research kind of says it all. The parallel method leads to significant improvements in traffic throughput, reducing congestion during peak hours. So, in plain English, it means more cars actually get where they're going faster, especially during that chaotic rush hour.
And wow, this chart just makes it crystal clear. That little bar on the left, that's what the old sequential method can handle. And the bar on the right, that's the parallel approach. The difference is just huge. We're not talking about a small, tiny improvement here. This is a massive leap forward. So what does all this tech talk mean in the real world? Well, it means the simulations run way, way faster. They use the computer's brain power much more efficiently, and this is the big one, they can scale up. So if a city's population doubles, this new model can handle it, no problem. And that brings us to our final section, smarter roads ahead. Let's pull all of this together and see what this amazing tech can mean for the future of our daily drive.
At the end of the day, this isn't just about playing some super advanced video game with virtual cars. It's about building a powerful tool, almost like a crystal ball, that lets city planners test out their big ideas before they spend millions of dollars building them. It could even lead to smart traffic systems that adapt on the fly to whatever's happening on the roads right now.
And that's the big idea I really want to leave you with. We now have the computing muscle to solve some of the most nightmarish traffic jams we can imagine in a computer. The next great challenge is figuring out how to take those brilliant solutions from the screen and make them a reality on our actual city streets.